Hello! It's been a little bit, and the world is kind of crazy right now. Hopefully, everybody enjoyed the extra week of spring break. I'm going to try to get a bunch of these lectures up this week since we're condensing the semester by just 1 week. So let's jump into it. So let's pick up where we left off with memory and alignment. This is lecture 7. Oh, always do that. Cool. So, let's talk a little bit about memory access. And I think some of you all saw this with the assignment to do with caching and how caches are essentially blocked, and it's a lot more efficient to sort of deal with the cache in terms of individual blocks versus individual addresses, because if you were at that granularity of individual addresses, things would start to get really weird and out of order, and you're keeping track more of things, and then that overhead becomes almost more significant than the memory that you're actually storing in cache. And in a way, the memory is much like a very, very large cache. And so if you can think about, memory, we don't generally address specific locations in memory. We address specific sections of memory. And that's what the memory gives us. So if we're asking for, say, memory location 7, we're not just going to get that piece of memory, we're going to get the memory around it as well in these chunks. And that chunk is what then gets placed into the cache, as we've discussed in previous lectures. And that's because the way that the processor deals with memory is not at the individual address level. It's actually in these sort of contiguous sections of memory. And this is because of the cost of individually accessing memory. And the assumption being that if you're accessing memory location 7, maybe you're going to address memory location 6 and 5 as well, per this particular slide. But if you address memory location 7, then you were trying to get 8, well, that's going to be a cache miss. The CPU is going to have to hit memory, bring in that chunk. So obviously this isn't a catch-all, but hopefully our chunks are big enough and our memory is fast enough that this happens less and less often over time. And so that's sort of the idea, is we are chunking our memory into these little sections, these pages. And so this is an important thing with regards to the previous example, where, say, I want to utilize my memory particularly efficiently. So think about this prior example, and say I have a 4-byte class or object, and if I put it in location 7, that's a pretty bad location to put that object, because it's going to be 1 byte of that second chunk and then 3 bytes of that third chunk, which means that every time I access that piece of that object, I'm going to have effectively a very likely cache miss, and that's not a very efficient way. But so how do we control that? How do we ensure that that object I put into memory, outside of legitimately hard coding the memory location for that object, how can we ensure that things line up against these sort of divisions? Because as you can see, if we can manage these divisions well, we can also manage how often we hit these cache misses, or at least alleviate a lot of them. And so that's where memory alignment really comes in. And the term memory alignment kind of discusses the idea of aligning our program and the architecture of our program to the underlying architecture, which generally is, you can essentially assume it's going to be memory aligned to 4, 8, 16, 32 bits, depends on your architecture. And so if your memory is not aligned, you'll see this sort of ladder example where we're going to be sort of in between these boundaries, and in some cases hit multiple boundaries. Whereas on the left side, if we're aligned to our memory, we're going to be much more within this. So in the left case, we're hitting 2 pages, and on the right case, we're actually hitting 3, which is a 33 or I guess 50% increase in cost, in potential efficiency cost, right? So yeah, memory alignment actually is a very important thing, especially with regards to streaming data, which is what we're essentially doing in every video game, because we're moving data from one place from the CPU to the GPU, from the CPU memory to the GPU memory, and sometimes in the opposite direction as well. And memory alignment also, really does affect how often we can do those bus transactions, because the bus wants to be fed all the time, and if we're waiting on memory, right, the whole kind of system just sort of chugs down a little bit. And so alignment is really critical to any GPU-based application, and in some cases, the APIs enforce this alignment for you, at least behind the scenes, or in some cases, don't allow you to use certain kinds of memory sizes that are not aligned. This is less common these days, but back in the day with OpenGL, for example, with textures were not only allowed to be in particular dimensions, and even today, to allow for arbitrary dimensions, the drivers do kind of hacks behind the scenes that are costing in memory to make up for alignment concerns because of the performance impact that they result in. So when you don't have aligned reads, a lot of bad things can happen. So for example, your software can run slower. That's just because you're missing the cache all the time, and it's slower. It can also cause applications to lock up, so it creates a lot of fragmentation, right? And sometimes things can't really fit into the spaces that we need them to fit in. Say your object is a 5 gigabyte thing and there's no space for it, and so if you're not utilizing your memory efficiently, the application can legitimately just sort of chug down and eventually not make any progress anymore. It can cause OS crashes, but I think this one's a little bit hand wavy. Like this really is a version of the second one, right? If sufficient number of applications lock up your system, eventually your operating system will crash. So yes, true, but a lot of things can be true, but in that sense. And also this is kind of true, right? It can cause software to silently fail, and that's largely because memory will overlap on itself and things kind of get wonky. But this one's pretty rare, and I've only seen it happen in rare occurrences, usually in like super high speed systems where you're talking about shared memory and things are kind of overlapped on top of each other, and if you're not doing aligned reads properly, then you can accidentally access something that you're not supposed to. But these days, that last one hardly ever happens because OS oversight is pretty significant. You'll get like a segmentation fault instead. So how unaligned data is handled. So what will happen here, right, when you load, say, memory, what will happen is you'll have to kind of get both. And then it's combined into one register. So in this case, say you're loading a memory location, you're gonna, load both of the bytes in this case, right? And then you're gonna have to shift them and then combine into a resulting final register. And this is if you're not doing 4-byte addressing. Sorry, the previous discussions I've been talking about are actually, I was talking about at the word level, but if you're actually doing sub-word, which is like 4 bytes, sub-word access, then you're now even costing yourself an additional, not only are you doing 2 loads for memory, so apart from the issues of memory alignment and caching and so on, you have to load 2 registers for memory and then combine them in a kind of a set of arithmetic operations, and then you get the final thing. And so in this case, it's almost like a 2x cost in terms of efficiency, because not only are you doing 2 loads, you're also doing 2 shifts, right? So that's 4 operations at this point, and then a combination, which is the 5th operation. And so versus just 1 load, if you were to be actually byte aligned to memory. So to ensure data alignment, what tools do we have in our kind of pocket? Well, you can actually explicitly do this. You can use DeclSpec Align 32. Also, Microsoft Visual Studio has the Pragma Push, pack and push thing, which is pretty effective. And what this does is it essentially tells the compiler, hey, whatever is in this sort of blob, in this little region, make sure that it's treated as if it's the size of 32. So it kind of just does a modulo 32 on it, and if there's any remainder, it packs on more padding, which is why in the case of the Microsoft Pragma, it's called pack, because you're literally packing on some empty padding. Also, yeah, so GCC can also use the attribute aligned thing. And in C++11, we have a line as and a line of, and then this is kind of trying to, as you can see, Microsoft has its own thing, and Clang has its own thing, and so all of the sort of C++ backends have accomplished this in different ways. So C++11 attempts to unify these in ways of a line as and a line of. You can also calculate it, so you can actually kind of hard code this if you're using, say, a type of a known size, which you can do by way of like using types instead of int and char. Instead, you could use uint8 underscore t or int 32, right? Like that value represents how many bits is in that particular data type. And if you have a struct of those things, and you can kind of do the mental calculus of like, okay, like two 32-bit shorts and and two cars, and then how much space do I have left? And so you can kind of construct a fully loaded struct that aligns to the memory architecture that you're using. And the way you do that is you have variables in that struct that may not be used. So if you've ever looked at an API, especially embedded APIs, use this pretty aggressively, where you have a struct and there's a couple of member variables that are like reserved 0 or reserved 1. You're like, what are they reserved for? They're actually there to pad that struct so that it fits the alignment of the architecture that you're on. So they're not actually reserved for anything. They're there and they have to take up space. And the API designer was like, well, instead of doing this at the compiler level and not being explicit, let's do it explicitly at the struct level. Then you're effectively not depending on a particular compiler to do it correctly for you. And again, like I said, this is much more common in C and embedded programming than in C++, where you're not as worried about that type of thing. But yeah, you can actually calculate it mentally and then design your struct or your class appropriately. So on that subject, how are these two structs different? On the left, you have char c and I char c. And on the right, you have int I char c char ch. So in both cases, if you're just looking at the memory size of these, you essentially have, each char is worth 1 byte, and the int is 4 bytes. Say we're on a 64-bit, on a 32-bit architecture. Sorry, well, ints are 32 bits on our architecture. So in this case, we've got 4 plus 6. We've got 6 bytes on the left. We've got 6 bytes on the right. And so in both cases, neither one of these are, byte aligned to the 4-byte boundary that we wanted to kind of hit. And so on the left, right, you can imagine we do this, and there's a sort of like invisible line that we have to draw somewhere. So say we're on a 4-byte architecture. So on the left, that line that we have to draw is sort of like halfway-ish on the int. So if we're accessing int I, we're actually going to have to hit 2 registers, two memory loads like we were talking about before. Whereas on the right, if we hit int I, that's only 1 register. If we hit int char c or char ch, that's only 1 register. So the right architecture is actually more efficient. But if you want it to be kind of explicit in that sense, you could always sort of pack it and design it a bit more explicitly, or use a union, or create some kind of padding. And so what this is really trying to show you is even the way that you order your variables sometimes really matters. Because if you put 1 byte in front of a 4-byte field, you're creating a lot of empty space or vacuum. So even the memory inside of a struct is something to kind of consider. So here's an example of in C++11 how you would use the align as, align of operators. And so in this case, you would for align as would replace the decal spec, the pragma pack, and all of that. And in fact, you can use align as inside of the class by defining, so for example, a char array 3, as the example was given in this previous slide. Well, that will pack that array with an additional byte so that the short below doesn't end up on that sort of like memory alignment boundary. And then align of will just give you the alignment of that object. and so you can use that to figure out what the alignment of objects are. So pretty useful. Little doohickeys in the past to actually support this in C++ is a bit of a pain per the varying C++ backends, but C++11 really kind of helped with that significantly. These things are compile time, not just align of, even kind of so align as, all the decal specs, the pragma, all that stuff happens in compile time. So this is not a runtime thing. Essentially, it just tells the compiler to treat these objects in this way, and to the programmer that looks like the same, but from the application level, it just looks like there's empty data. So you're kind of solving this problem with memory in a way. So if you're very, very memory constrained, this is not necessarily the best option. You really have to reconsider how you're designing your application in the first place. But align of is a compile time thing as well. It just looks at the definition of that and then figures it out. And so, if you're trying to test your own alignment, you can also do this in this way, because this is a runtime thing, where you want to make sure that your data, the last byte of your data, is I'm not actually too familiar with this. One moment, I will pause. Okay, sorry, I just had to look this up because I've seen this before and I just wanted to make sure I understood it enough to explain. So what's happening in this line of code, and the reason that this allows you to determine whether a pointer essentially is, or your data by way of a dereference, but by way of a reference, it is aligned, is because what is happening here is first you're taking the address of your data and converting that into a pointer, into a pointer, and that's a value, and the pointer value then, the last bits, the last 8 bits of the nibble should essentially be 0 if you're memory aligned, and that has to do with the fact that if it's not, then you're in the middle of that. You're between that 16 byte boundary, because the last nibble represents 16, right? The last 16. So if it's 0, then you're right on that boundary, so you're aligned. If it's, say, on byte 5 of that boundary, that value will be 5. And so this way you can actually take a look at the memory address of your data, convert it into an integer. So you're not dereferencing the pointer, you're just looking at the value of the pointer. Because if you were to actually dereference the pointer, then you would load from memory and you would not be able to determine anything by the value. But what you're actually doing here is you're taking the value of the pointer, converting it into an integer, just the value, and then looking at its last few bytes, and its last few bits, really, to understand whether or not we're on that byte boundary. And so whether using 0xof or the value 15, it doesn't really matter. Essentially, you're figuring out, does my memory location start in a multiple of 16? So you can also do this with a modulo operator as well. Whoops. Cool. So you can also do this with other alignments, obviously with 64. Again, you can just not even do the AND, you can just do the modulo if you know the alignment. And this way you can ensure that you are doing an aligned malloc by way of figuring out the location, your alignment, and the size. And so to kind of go through this bottom function, this aligned malloc function, right, will figure out the required bytes. If you give it the required bytes and the alignment, you have these 2 pointers, one of which is going to, your offset's going to be the alignment -1 plus the size of a void, which is the size of the pointer. And then what you're doing is you're essentially going to malloc the required bytes plus the offset, which is the potential amount by which you might have to sway your memory location. And then P2 then accommodates that by way of taking a look at the value of P1 and removing from it that those last bits. I'm not answering this very well, but like essentially you're taking a bunch of memory and then you're kind of like shifting up a little bit to make up for wherever you land on that boundary. So like making sure that P2 is going to be at that boundary, or modulo 64 of the value of P2 or whatever the alignment value is. It'll give you exactly the value that you want, which is cool because you can't necessarily trust the heap to give you a memory aligned address. So this is sort of just a bit of an insurance of that. But keep in mind, right, in this case, we have allocated more data than we're using. And what that means is you're going to have to deal with that in P1. So you can't like hack into that memory. When you're deleting and deallocating memory, you have to kind of think about the implications of that. So you have to kind of hold on to both. Um, so if we want to really manage our heap, right, then we kind of want to potentially override new and delete. And to do that, it'd be nice not to have to do it ourselves. We kind of want to have an intrinsic call. So is there a better alternative? Apparently there is. In C++11, we can use aligned storage, which is a new thing, something that I haven't used too much of personally, but can be very, very helpful. Yeah. So to talk a little bit about branching, because branching is another place where we spend a lot of time. So obviously a big performance impact to our program is loading from memory because we're doing that a lot. But almost every application has a branch in it. In fact, I'd say that every application has a branch in it just by virtue of launching the application, which is a branch in of itself. A branch is essentially defined just as a jump in one location of memory to another, and to do anything on a computer, we are doing that. So there is kind of this intimate link between branching and memory access by way of the fact that when you branch, you are just literally going to a different place in memory and having to load it. So the two are kind of both the levers we can pull to improve the quality and speed of the program. And so it's very inefficient to branch too much. It costs us a lot. We can hit instruction cache misses and have to load stuff from memory. We can run and be in CPU more than we need to necessarily be. Many branches actually can be optimized out. So if you've ever written shader code, you've probably seen things and variables disappear that you were like, hey, but I wrote that variable, this error doesn't make any sense. But that's because the shader compiler said, oh, this variable actually never gets used, and it just gets, or this branch path never gets, followed because of the condition never gets, correct, and so it just deletes that code, and as a result, your variable goes away. When you try to read it, then you have an error. Well, that's why, because shaders really have to be super efficient because they're running once per pixel in some cases, and so those compilers are super aggressive in optimizing out any code or any bit that is not being used. And so to understand some of the branching that we're going to talk about, you have to understand bitwise operations, bit shifting, and unsigned and signed values, which should be very familiar because we've talked a lot about those already. So branches happen whenever you make a decision. So anytime you're saying left or right, that's a branch, right? Or a fork in the road. Although we don't use fork because that's, a word we use for a different purpose in computing. And so, for example, a branch includes the ternary operator, which is the question mark and the two options, as well as, and ternary is probably less often encountered in like C++, but it's very, very common in C, and it's pretty useful because sometimes it's a little bit more of an efficient, makes more sense. Like I want this to be equal to this thing in this case or that case, and you don't have to have multiple, definitions, and it's a little bit more efficient in some cases. Branches take longer in terms of cycles, obviously because we have to spend some time evaluating the condition and also jumping to the appropriate branch, and that all takes time and you have to load from memory. What's really nice with CPUs, as we talked about before, we have branch prediction hardware. In many cases, a CPU will kind of go in both directions, and then we'll figure out what the condition is and then decide, okay, this is the direction I want to go, cancel out the previous branch. But it's a little bit harder to do, with nested branches. So if you have a branch within a branch, you know, it starts to become a dream within a dream, and Incepticon kind of fails. So nested branches are a little bit less easy to deal with. And it also, obviously, if we mispredict and we went down this path and then ended up that the condition failed and we have to go back and start over, or we have to flush the pipeline. So it's not always the most efficient. So branching is kind of, you know, a mixed bag. It's more of a statistical kind of thing sometimes. And it also is pretty bad, like if you have like a inner loop type of situation where the branches run no matter what, and very often where branch prediction can sort of cost us a lot because it's statistical in some nature. And if you know if the program knows it's going to be taking a branch, but the branch prediction hardware is like, I don't know, right? And so you've kind of got these two opposing forces, and say some percentage of the time it's going to take the wrong branch prediction, even though we know from a program design standpoint that it's always going to go down that path. So you're just giving up like some percentage of performance per the cost that it takes to make the wrong prediction. So yeah, all these things are considerations to be taken when you're writing a program. One thing you can do, obviously, to help your program is get rid of conditionals. So one great way to not have branches, to improve your branching efficiency, is to not have branches in the first place. So how could we, in theory, remove this conditional? And like, can you even get rid of the conditional here, right? Ultimately, we sort of have to think about what's happening in this particular case, right? We're not really, it's less that we are setting, you know, taking a branch as much as setting a value of a variable conditional to the values of two other variables. In a way, that is kind of like, you know, basically having an operator, right? So if x is less than y, do equals 1 equals 0. In fact, like a very simple way to do this, just by way of getting rid of the if, but not actually, it won't actually get rid of the conditional. It depends on your architecture. You can literally say grow equals x less than y, because what happens on many ALUs, you have a comparator function, and so it's going to evaluate x minus y, x is less than y, set that in a register, and then pass it to grow. So that alone is one way to get rid of this, you know, this branch. But it's not entirely true on all CPUs, because if you don't have a comparator function, you may not get that benefit. There are other ways to do it, like with bitwise. You know, and say this is not just what we want to do. We don't want to just have x less than y. What if we have a lot of things? So say we have x less than x1, x2, and so on. So there are ways to eliminate branches. For example, there's a link here. You can check it out. Well, I guess how do I, here, I can disappear, and you can see that link right there. Cool. Okay, so yeah, so let's say we have this sort of more like a not a nested, but a sort of sequential, almost like a case switch statement kind of thing. In this case, we're literally comparing x to a particular set of values. And the graphic representation here is, say x is less than x1, then we're going to be a0. So we're going to be here. So if we're less than a0, right? For the next one, if it's less than x2, that also means that it's greater than x1, right? Because this first one failed, and it's going to go on to the next one. And that means we're going to be in A1. And then the value that we pass is alpha1, or in this case, alpha1, and so on and so forth. So we can kind of create this thing, and with a final conditional suggesting that we're over that value. And so the way we can do that is basically going through this wacky code, and it uses a bunch of shifts and things to accomplish it. And so you can kind of see again what I was saying before. A lot of this is essentially just utilizing operators to figure out where we are. And in this case, so if x is less than x1 in this case, and so in each one of these cases you can see x, lt, x1, and x2, and so on, we're taking the difference between x and that particular value, and then we shift all into the ones, and that's really what we're doing here is we're determining whether or not the value, the sign bit of this is 1 or 0, which tells us if it's less than that, if the x is less than x1, then the result here is going to be less than 0, and that sign bit will be 1. And so in this case, you can see x1, x2, x3. If say x4 is true, so x is greater than x4, but less than x3, then x4 will be 1, and the rest of these will be 0. So we can, but if it's say, greater than x1, but lesser than 2, right? We'll actually see, this be 0, and these be 1s. So sorry, that it's inverted. If x is less than, it'll be 1. So in the case of it being greater than x1, then that'll be 0, and x2 will be 1, x3 will be 1, x4 will be 1. And if it's greater than x4, then all of these will be 0. And then you can essentially create bitwise logic, such as, for example, if x0, if a result is 0, then we're going to have, if we're going to AND a3 with x4, or it's not x4 and a4, and so on. Hold on. I guess this is a combination. This will only keep the variable that has all ones in it. So this is just sort of that combination. Oh, I see. We are shifting these to 31. So what it's doing is it's not just 1, it's not the value 1, it's all 1s. And so this AND becomes much like a logical AND versus a bitwise AND. Sorry, that got me off for a second here. And so what we're doing is we're kind of doing the combination of everything and also nesting them to figure out in the final result the value that remains is the one that is logically out of these correct. If you guys want me to go through this in a deeper way, if that's required, please let me know in Discord. I'm happy to kind of dig into it deeper. But if you follow the logic here, essentially, if xlt4 is true, then we get 3 and not 4, right? And so on and so forth. So in this way, we can kind of basically cascade them down, if that makes any sense. Cool. Hope that makes sense to everybody. Great. Not all conditionals can obviously be optimized this way. It really has to do with specifically what you're functionally trying to accomplish. Like in this case, again, it's very specifically this kind of mathematical operation, and you can't necessarily always do that. It's also very not readable. Comments can help, and obviously you can inline and define functions and so on. But just like I just tripped all over this thing to try to explain what's going on. If you're trying to read through somebody's code and you see this, you'd be like, what the fuck is this? So it's not very readable. Even if you comment, people don't read comments. So you hardly ever see this in practice. Here's a different approach to avoiding branches, right? In this case, we, again, are getting the sign bit of the value a. If it's negative, it's 0. If it's 0, it's not negative. If it's negative 1, if it is. And then we do the 1's complement if it's negative, plus 1. And that way, what we're essentially doing here is we're essentially avoiding the if less than 0, then multiply by negative 1, and so on. And so this is kind of instead a way to do it without having to kind of go through that branch. But again, as you can see in this pattern, this thing is wrapped up inside of a function that is a critical path kind of function, right? The absolute value of a variable is something that we may be doing many, many times per frame or many times per second. And so this kind of thing makes sense to try to optimize, but it's still wrapped up in a logical unit that makes a lot of sense. So even though all this commenting is easy to understand, you have to kind of stop and understand what's going on here. If this was part of code instead of inside of a function, you'd be like, what's really going on? Whereas if I'm calling this in a different function, no big deal, right? And if I do want to see the implementation, I can go to that code and understand it. But if I don't ever read this, it's no big deal at all. So, vtable. This is kind of a bit of a jump, but vtable is an interesting subject. Vtable is how we accomplish polymorphism in C++, which is essentially inheritance, right? Being able to have an object that then inherits from a child object that inherits from a parent object, a bunch of different functions and capabilities and structure and so on. But there is a cost. Polymorphism is not free. It's not a static time thing. It's actually a runtime thing. And so you do have to pay some cost both in performance and in memory. And so let's kind of talk about what that looks like. This slide mentions a example which I do not have, and if this is something that you all are really kind of keen on seeing in practice, please let me know and I can put something together. But let me know. There was nothing available in the curriculum that I was provided with, but we're going to talk about it without looking at code. But if you'd like to see some code on the subject, let me know and I can put an example together. So to talk a little bit about virtual functions, basically the way virtual functions are accomplished in C++ specifically is what's called the vtable. It's a table of functions that determine which function should be called. So when you have a base object, and if you call that particular base object, say it has a print function, it's going to call specifically that function, which is just a piece of memory, instruction memory that is being pulled from somewhere. If that class then has a child that then inherits from that object, if you call that print function, and it's not overloaded in this case, then it's going to just call the base function, and so you don't have any cost really, because it's going to that function, it's resolving which one to call, and there is no vtable for that function, and so it just goes straight to the function and it works. And so you're kind of static in that sense. However, if that object then underline is able to, and this is by the way why you have to define virtual functions, because if you don't define it, I mean, the compiler will do it automatically for you in the background, but generally speaking, it's a good practice to write virtual, because then you kind of create the vtable anyways, and you're already paying that performance cost up front, but maybe the compiler will optimize it out for you, but it's a good practice anyways. But if you subclass that object and then you override that function, when you call that function at runtime, right, it goes to this vtable that then determines which function is the correct one to call. So say you have an object called fruit, and then another object called apple that inherits fruit, right? And they both have print functions, right? You may have, fruit, like a new fruit object equals new apple, right? And then you call fruit fruit print. It's not going to go to the fruit print. It's going to go to the apples print. And how does it know to do that? Well, it hits that vtable and knows, oh, okay, the value of this vtable entry, which is just a variable, right, is this other location versus my original value. And so that takes up memory. So it's actually held in the object itself, much like a member variable. In fact, you can accomplish the exact same thing by using a pointer function ultimately, right? If you have a pointer function, a function pointer, and you call that function pointer, it's going to call whatever function is attached to that function pointer. So that's essentially what this all is. So you need an extra pointer that needs to be dereferenced. So that takes up a little bit of performance, but that's not what is actually taking up the performance cost, usually, of virtual functions. Say we're in a part of instruction memory and that function pointer, the vtable function pointer, is in some other wackadoodle place. Well, now we have a cache miss, or an instruction cache miss, and the program has to load from memory something that wasn't already there, and that takes time, right? And so that's why, in this previous example that I'm supposed to show you, when you have optimization, the program will optimize memory and put things in the right place so that that cache miss doesn't happen as often. When you turn off optimization, those things go away, and as a result, you may be hitting instruction cache misses all over the place, and it can be very expensive. Another cost of the vtable is when you turn on optimization, any short method may kind of turn into inlining. But if the method is virtual, it will never get inlined. So if you're turning on optimization and you're trying to like improve your code base by way of the compiler, virtual functions will never actually benefit from that. And so, yeah, because the compiler basically doesn't know. It'll never be able to assume that something should be inlined because, even like say the print example, right? The print example could be in theory inline. It's only one line of code. I know that's not really what is going on, but imagine it's like a +1 type of thing, and then a inherited object may be a much more complicated function. But that original thing that maybe is getting hit a lot will never get inlined, even though in theory we might be hitting it millions of times, and it'll never quite go away. So why are these good? Why would we ever use virtualization? Well, first of all, if you're only using one virtual function, like it never gets overridden, it's going to get optimized out. So that's good. One thing that's really good about C++, even though in unoptimized debug mode everything seems to be slow and crappy, the kind of overall goal of C++ is with all of these features to be as fast as C. That's not always true, as we all know, but that's the goal. And so a lot of these, specifically the C++ core language features like polymorphism, are never okay. They're never done unless they're comparable to C in speed. So virtual functions are really powerful, especially when you're dealing with something like you're trying to build a platform where, say, you have multiple implementations of the same object. Say, like you want to implement OpenGL and DirectX, right? But you want to, develop for both using the same interface, right? So I don't have to write different code for OpenGL than DirectX, and you design this what's called a hardware abstraction layer, right? And all that kind of thing. And so, yeah, this way your implementation is encapsulated and separated from your actual code, like your actual intention or your functions. And so it's quite powerful, and very often it's completely okay to pay this performance cost. And generally, when you optimize your code, the cost of that goes away anyways, right? And it's a little bit more efficient. Like, for example, we talk a lot about branching, and branching is no good, right? But dereferencing a pointer to instruction memory is better than branching. Ultimately, you do have to branch to that location in memory as in a jump, but it's not like you're predicting there's no prediction, there's no branch prediction, so it's more efficient than that in that way. Often, and this is maybe a flame war in the making, but I tend to advocate smart, intelligent architecture over kind of nitpicky performance improvements, because you can always add the nitpicky performance improvements when you're shipping code, but when you're designing code, you really should design it well and flexibly and easy to understand, and kind of with a more kind of bigger mindset, because you build the thing and it works the way you want it to, but then you need that extra 2% of performance to kind of get over that bar so you can ship. Well, you spend a week before you ship getting over that bar, right? But to do that, to make that possible, where you can just spend a couple of weeks at the end before shipping, you need to design your code intelligently in an architectural way that allows for you to kind of go in here and understand where you have performance problems and where memory is being lost or not used efficiently and so on. So yeah, this class is about designing large-scale systems, and ultimately large-scale systems are never written optimization first. But with that said, in the same breath, optimize early and often when you can. So don't throw virtual windows out the window because they're like a slight bit slower than inline functions, but make sure you know what you're doing when you're using them. there's an alternative approach to a lot of this stuff, which is generic programming in the way of templates and all that. But that's what you make up for in performance, you lose in like build times. And it takes a really long time sometimes to generate that code. And you know, so it's a push and pull. Like everything in coding and development in general, there's always sort of this balance between how long does it take to build, how hard is it to deploy, how easy is it to understand, blah 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 blah. So always kind of keep that in mind. Here's kind of a quick example. As I was saying, right, we have a base class and then two D1 and D2 that override function 1 and function 2 in this case, and this is sort of the way that the vtable looks in both cases, right? You have a vtable for the base class, you have a vtable for D1 and for D2. And I should mention, right, the D1 and D2 and the base class, these are instances because these are runtime variables. So those actually do exist in memory as well as the function pointer, which is kind of an interesting thing to kind of keep track of. Yeah, and that's it. Oh, I guess I don't have the final slide. And that's it for memory, alignment, and other subjects. Cool. Thank you for watching.